Good day, everyone. Today, I will present and discuss the proof of exercise number 13A in Abstract Algebra. In this presentation, I will explain the important definitions related to ring homomorphisms, ideals, kernels, and inverse images. After that, I will discuss the proof step by step. This presentation is divided into 6 parts. First, we will begin with introduction to the topic. Second, we will state the theorem that we want to prove. Third, we will review the preliminary concepts and definition needed for understanding the theorem, including rings, ring homomorphisms, ideals, kernels, and inverse images. Fourth, we will proceed to the proof of the theorem step by step. And we will summarize the important conclusion obtained from the proof. In ring theory, homomorphisms are functions that preserve the operation of rings, specifically addition and multiplication. Ideals, on the other hand, are special subsets of rings that play an important role in constructing quotient rings and studying algebraic structures. One important property of ring homomorphisms is that the inverse image of an ideal under a homomorphism remains an ideal. More formally, if F from R to S is a ring homomorphism and J is an ideal of S, then the inverse image F inverse of J is an ideal of R containing the kernel of F. Now, let us formally state the theorem. Let F from R to S be a homomorphism of rings, and let G be an ideal of S. Then F inverse of J equals the set of all elements are in R such that F of R belongs to J is an ideal of R containing the kernel of F. In simpler terms, every element of R whose image under F belongs to G forms an ideal in R, and the kernel of the homomorphism is always included in that set. To prove the theorem, we divide the proof into 2 major parts. First, we prove that the inverse image F inverse of J is an ideal of R. Second, we prove that the kernel of the homomorphism is contained in the inverse image, meaning the kernel of F is a subset of F inverse of J. Before proceeding to the proof, let us first review the basic definitions. A ring R is a set equipped with 2 binary operations, addition and multiplication. A ring must satisfy 3 important properties. First, under addition, the set forms of an abelian group. This means addition is associative and commutative. There is an additive identity, and every element has an additive inverse. Second, multiplication is associative. Third, multiplication distributes over addition from both the left and the right. A ring homomorphism is a function between 2 rings that preserves ring operations. If F from R to S is a ring homomorphism, then for all elements A and B in R, the following conditions hold: F of A plus B equals FA plus FB, and F of AB equals FA times FB. Also, the homomorphism maps the 0 element of R to the 0 element of S. This means that the structure of the ring is preserved under the mapping. Next, let us define an ideal. A subset J of a ring S is called an ideal if it satisfies 2 conditions. First, J is closed under subtraction. This means that whatever A and B belong to J, then A minus B belongs to J. Second, J absorbs multiplication by elements of the ring. This means that for every S in S and every A in J, both SA belongs to J and AS belongs to J. The kernel of a ring homomorphism is the set of all elements in R that map to 0 and S. Formally, the kernel of F equals the set of all elements R in R such that FR equals 0 and S. The kernel measures how much information is lost under the homomorphism. Next, the inverse image or pre-image of a subset J of S is defined as F inverse of J equals the set of all elements R in R such that FR belongs to J. In other words, it consists of all elements in R whose images belong to J. We now begin the proof of the theorem. So our goal is to prove two things. First, that the inverse image is an ideal of R, and second, that the kernel is contained in the inverse image. To show that the inverse image is an ideal, we must verify three conditions. First, the set is non-empty. Second, it is closed under subtraction. Third, it absorbs multiplication by arbitrary elements of R. For the first step, we show that the inverse image is non-empty. Since J is an ideal of S, it must contain the zero element of S. Because F is a ring homomorphism, it preserves 0. So F of 0 in R equals 0 in S. Since 0 in S belongs to J, it follows that F of 0 in R belongs to J. Therefore, by definition of inverse image, 0 in R belongs to F inverse of J. Hence, the inverse image is non-empty. Next, we prove closure under subtraction. Take any two elements A and B belong to F inverse of J. By definition of inverse image, this means FA and FB belong to J. Since J is an ideal and ideals are closed under subtraction, we obtain if A minus FB belongs to J. Because F is a ring homomorphism, it preserves subtraction. Therefore, f of A minus B equals FA minus FB. Since FA minus FB belongs to J, it follows that f of A minus B belongs to J. Hence, by definition of inverse image, A minus B belongs to F inverse of J. Therefore, the inverse image is closed under subtraction. We now prove absorption under multiplication. Let R belongs to R and A belongs to F inverse of J. Since A belongs to the inverse image, we know that if A belongs to J. Using the homomorphism property, f of RA equals FR times FA. Because J is an ideal and absorbs multiplication, we obtain FR times FA belongs to J. Since FRA belongs to J, it follows that RA belongs to F inverse of J. Similarly, we can show that AR belongs to F inverse of J. Therefore, the inverse image absorbs multiplication by arbitrary elements of R. Thus, all the conditions for being an ideal are satisfied. At this point, we have shown that the inverse image is non-empty, closed under subtraction, and absorbs multiplication. Therefore, we conclude that F inverse of J is an ideal of R. We now prove the second part of the theorem. Take any element X belongs to the kernel of F. By definition of kernel, f of x equals 0 in S. Since J is an ideal of S, it must contain the 0 element. Hence, 0 in S belongs to J. Therefore, fx belongs to J. Since the image of X belongs to J, by definition of inverse image, we conclude that X belongs to F inverse of J, because every element of the kernel belongs to the inverse image. We obtain the kernel of F is a subset of F inverse of J. So this completes the proof of the theorem. To conclude, we prove that for a ring homomorphism F from R to S and an ideal J of S, the inverse image F inverse of J satisfies all the properties of an ideal in R. We also prove that every element in the kernel maps to 0 in S, and since 0 belongs to every ideal, the kernel must be contained in the inverse image. Therefore, F inverse of J is an ideal of R containing the kernel of F.